Dear students, we are all familiar with the words work, energy and power. When a teacher is teaching, student is studying, or a man pushing a table, in all these cases they are said to be working. But in physics or in science, work has a very precise meaning. The meaning of work in physics is very much different from the picture that arises in our mind when we hear the word work in daily life. For example, if someone is only sitting at one place and that someone is keeps on reading for some amount of time, that is no work in terms of physics. Perhaps it can be considered to be a mental work but not physical work. Sometimes in order to assess the efficiency of person or people, we compare the work done by two or more person in the same period of time, right? So that is the ability to do work, that is related to energy, that is related to power. So these things we are going to study in this chapter. Let us start with the topics that we are going to study in this chapter: introduction, work energy theorem, work, kinetic energy, work done by variable force, potential energy, conservation of mechanical energy, potential energy of a spring, various forms of energy, power, and we will study collisions, elastic inelastic collisions in the last. In that, for this year, only one topic is removed, that is various forms of energy, but we shall try to go through that topic as well. Now, starting with the scalar product. Now, why we are studying scalar product? Because you see, whenever we want to develop an understanding related to work, energy, and power, we need to develop the mathematical processing, namely the scalar product of vectors. Right? To understand work, energy, power better, we need to know about the scalar product, and that will help us to calculate the numericals as well in this chapter. Also, in future purpose, whenever you are doing a multiplication of the products of two vectors, that will also be helpful. So you see, physical quantities like displacement, velocity, acceleration, all were vectors. We have already studied in chapter 3 especially, and 4 we studied about addition and subtraction of vectors. Now in this chapter we will have to learn about their product, that is multiplication. So there are two ways in which we can find the product. One is scalar product, second is vector product. Now scalar product we will study in detail in this chapter, and vector product we might study in detail in chapter 7 when we will start chapter 7. Okay. So right now we will focus on the scalar product. So what is scalar product? Scalar product of two vectors, that is A and B, is defined as A dot B. You might have known that in mathematics a dot means multiplication. Okay, so A dot B is magnitude of A, magnitude of B into cos theta. Now you see how this comes into picture. We have a vector A and vector B. Okay, in the vector B, you can see the slight projection of vector A. Angle is theta, so that projection will be the x component of A, that is A cos theta, right? So what is A into B, A dot B? That is AB cos theta. You know that magnitude of any vector is written just by the capital letters only. So what is the scalar product? It is A dot B cos theta, and theta is the angle between vectors. Now in between, instead of multiplication sign we are putting dot, that is why scalar product is also known as dot product. Geometrically it can be said that the scalar product of two vectors is equal to the product of magnitude of first vector with the projection of second vector on the first vector. That is why we are seeing this figure A cos theta, projection of A on B. Now let us see few properties of scalar product. Scalar product follows commutative law, that is A dot B equals to B dot A. So if you do the scalar product keeping A vector first and then B vector, and also B vector first and then A vector, the product will be the same. Scalar product also follows distributive law. If there are three vectors, you can always prove this formula. A dot B plus C is equal to A dot B plus A dot C. So distributive law is followed. If A is parallel to B, that means theta is 0 degree, then A dot B equals to AB cos 0, that is A dot B only, because cos 0 is 1. If A is perpendicular to B, theta equals to 90, then A dot B equals to A dot B cos 90. Cos 90 is 0, so whole product will become 0. Scalar product of unit vectors in Cartesian coordinate system. So let us talk about I, J and K. So if you multiply I dot I or J dot J or K dot K, that all will become 1. Okay, that means if you are multiplying 4I dot 4I, that means the result will be only 16, because I dot I will become 1. But if you multiply the perpendicular unit vectors, for example I dot J or J dot K or K dot I, the whole product will be 0. Clear? So these two rules you keep in mind. Now continuing with the properties of scalar product, let us suppose that we have a vector A given in terms of its components AXI plus AYJ plus AZK. Another vector is B, again with components BXI plus BYJ plus BZK. Now what will be A dot B then? So that will be whole A component dot B components, and now you see the next topic very carefully. Next step, only X component will be together, then Y component will be together, then Z component will be together, and in between we will have addition. So it is AXI into BXI plus AYJ dot BYJ plus AZK dot BZ. Now as I said, I dot I, J dot J, K dot K will become 1. So our final answer will be AX BX, AY BY, AZ BZ. Clear? Now how to find out the angle between two vectors? So there is a special formula for angle between two vectors. See carefully. A dot B equals to magnitude of A dot magnitude of B cos theta. So if we can make a formula for cos theta, how shall it be? Cos theta equals to A dot B upon magnitude of A into magnitude of B, and we all know how to find out magnitude of any vector. The square of all the components, and you do the sum, finally you do the square root. So this shall be the magnitude. Take care that the AY2 written over here is not 2, actually it is square. In both the cases you see this as square. Okay, AX square plus BX square, AX square plus AY square plus AZ square, BX square plus BY square plus BZ square. Okay, so this is the way to find out angle between two vectors. Now moving further, let us see about work. Work is said to be done whenever a force acts on a body and the body moves through some distance in the direction of force. So you see, two things are very necessary, right? Force must be acting and the body must be moving. Then and only then work is said to be done. For example, horse pulling a cart, engine pulling a train, etc. Now measurement of work done when the force act along the direction of motion. Suppose motion is in east direction and force is also in the east direction. So what shall we do? Let us suppose that force F displaces a body through distance D. So what shall be the work done? W equals to F dot D. Simple, right? No angle is involved because force and direction both are in the same case. Now if in case second number, sorry, measurement of work done when force and displacement are inclined to each other. What do you mean by the word inclined? Inclined means at an angle. So in that case we have to see the figure very carefully. You see, force is acting at an angle, but you see if the direction is towards the right side, we will take only the component of force which is towards the right side, right? That means F cos theta will be taken. So what shall be the formula? W equals to F cos theta into D, where work is F cos theta, that is component of force in direction of displacement into the magnitude of displacement. Clear? And remember that work done is a scalar quantity. Now, nature of work. So based on different nature of work, different values or different direction of motion that is being done while working, we can divide the work into positive, negative and zero work. So what is positive work? If a force acting on a body has component in the direction of displacement, then work done is positive, right? When the body falls freely under gravity, when a horse pulls a cart, when a spring is stretched, right? So these are few examples of positive work. What is negative work? If force is acting and the body has a component in the opposite direction of displacement. So force and displacement both are opposite. For example, brakes are applied in the moving vehicle, body is lifted working against the gravitational force. So these are the example of negative work. What is zero work? Work done by the force is zero if the body gets displaced along a direction perpendicular to the direction of applied force. Also, if in case there is no displacement or no force acting, then also the overall work done will be zero. But perpendicular, you see centripetal force when a body moves in a circular path, the centripetal force and displacement are perpendicular. So we can say that work done by centripetal force is zero. Also, one very nice example, when a coolie walks on a horizontal platform with a load on his head, right? Load is acting downward, but the coolie is moving in horizontal direction. So work done by the coolie on the load is zero, right? So positive, negative and zero work. Now, dimensions and units of work. Work done equals to force into distance. We know that the dimension of force is m1 l1 t minus 2 into l1. L1 is the distance. So only L is to be calculated and that will be m1 l2 t minus 2. So this is the dimension of work. What is the unit? Newton into meter, because force is Newton, distance is meter. Or we have a special unit named after a British physicist James Prescott, Joule. So we are naming Newton meter as Joule. And now, what is 1 Joule work? So put 1 in front of Newton and meter, you will get the definition. When a force of 1 Newton displaces a body through 1 meter in the direction, 1 Joule work is said to be done. Now 1 Joule is 1 Newton into 1 meter. CGS unit, SI unit we have seen Newton meter or Joule, but CGS unit is erg, ERG, smaller unit. You see the relation 1 Joule equals to 10 raised to 7 erg. Okay, so these were the dimensions and units of work. In the next videos we shall continue further, right? So till then you see this video and make proper notes. Thank you.